All right. This talk is about the feedback loops that we experience as programmers. I'm going to talk about what they are, how they affect us, and how we can do better. A feedback loop is formed when an action causes an effect, which prompts another action, which causes another effect, and so on. A lot of people associate the word feedback with Jimi Hendrix. This scene contains two feedback loops. The first is between the guitar and the speaker of the amplifier. The vibrating strings cause the amplifier to emit sound, which in turn vibrates the strings more, causing more sound, and round it goes, and if left unchecked, it results in an unbearable squealing sound. But this talk is more about the second feedback loop, which is between Jimi Hendrix's brain and the music he's making. My interpretation of this scene is that Jimi is working to harness that squealing sound. As the sound hits his ears, he's making tiny adjustments to the guitar, thereby creating music. The feedback loop for a typical web developer is not quite so glamorous. It might look something like this. You get asked to fix a bug or make a feature, so you go and change some code. You save your file or files, recompile your application, swap to your browser, reload the page, have a poke around, see if it seems successful, and if it wasn't successful, try and figure out what went wrong. You might use like a debugger or a process of induction or something, but it will probably lead you back to changing yet more code. This code makes light of an extreme scenario, which tragically is still common today. Although the occasional sword fight can be fun, I still think that we should strive to be more like Jimi Hendrix when we program. Why should we bother to make our feedback loops fast? The first reason is that programmers are creative people who, like artists, do not respond well to boredom or tedium. A slow compilation or testing step breaks our flow and pulls us out of the zone. It can also be very difficult to predict the behavior of code. It's safer to make our changes in small increments so that we're able to match up the cause with the effect. A slow feedback loop encourages us to change multiple things at once. This can leave us befuddled when things don't go as planned. Finally, we want to finish our day with a sense of accomplishment. We don't want to feel like we spent the whole day waiting for dumb, slow tools. To get some perspective, let's have a look at the slowest feedback loop in programming history. Before the microcomputer revolution of the 80s, computers were astronomically expensive to buy and maintain. Usually they were capable of running only a single program at once. Most commercial programs did bulk data processing. They were batched so that minimal computing time was wasted. So you'd have one program run, used up all the resources of the computer, ran to completion, and then you'd start another program. Does anyone know what these are? Everyone knows what these are, that's nice. But I'll hand them around because I don't know how many of you have felt one in the flesh. Has anyone actually used punch cards here? No. I was born in 1991. I bought them off eBay.
How much do they cost?
Not very much.
Okay, I wasn't sure whether that did
Some might be worth more. They might be a collector's item. I don't know. Anyway, batch processing made use of a primitive storage medium to communicate data and programs to the computer. Think of a punch card like a floppy disk that can only hold a single line of source code. The computer reads the holes, and humans read the text printed along the top. Each column of holes encodes a single character. Can someone tell me how many columns there are on those cards?
I'm going to guess 255.
Have a look. 80.
80 on that one. Ooh, yeah.
That's the origin of our line limit. Yeah, that's the line limit we use today, right?
Oh, it does say it.
It says it on the cards too. Look at your card.
That's the origin of our what? 80. Yeah, 80. Okay. So this turned into terminals and then like.
So what? This is 10 bytes. No.
It's 80 characters.
80 characters.
So you see this P is encoded. This P is encoded with these two holes. The space is encoded with no holes. The star is encoded with these 3 holes. And that's the encoding system. That was all they could do. That was the only thing they had that was reliable enough.
Printed the characters along the top.
They're printed along for like.
So is this ASCII then? Like if we go and look at one of them.
It'll be a subset of ASCII, capitals only.
Okay. Yeah, cool.
So the 80.
Yeah, because it'll be the 127. What we got.
It'd be less, significantly less.
So the 80 character lines are big because the first terminal is effectively mapping punch cards.
If a programmer wanted to run their program on a computer, they had to generate a stack of punch cards using a key punch machine. Each card had to be typed out by hand with no mistakes.
Probably still more reliable than one.
Well, there was a certain space disaster that you should look into. When it came to debugging, programmers had to compete with other batch jobs for precious computer time. Programs were written offline and submitted to the operations team, which scheduled them to run. The printed output was returned to the programmer. That might be the textual output of your program. It could be compiler errors, or it could be a memory dump in hexadecimal. And that's what these guys used to have to look through to debug their programs.
So they get the memory dump. How would they get that?
They get given back from the operations team.
Oh, yeah, of course, yeah.
The dot matrix printed, so
Yeah.
Oh, that hex.
Yeah, it's like program and data goes into the computer, output comes out, and it might, if there's a crash, it'll be a memory dump.
Yeah, he's memory dump.
Yeah, so they had to, like, programmers had to look through those memory dumps, figure out what all the hexadecimal values mean, and like infer what happened with their program.
Ah, it was this one down here that should have been something else.
I don't know. I bow down to these guys.
Yeah. Although in our defense, they were only looking at, that much code rather than something that compiled into like a megabyte minimum these days.
Still be pretty hard.
It would be.
This is a video I want to show you guys. He's carrying stacks of punch cards.
There's those punch tape as well, which is like a roll of tape rather than individual cards.
This is the operations room. So you handed in your program here. He's scheduling it to run on the 7090 computer. You could have a sword fight right now.
Yeah, it should be miniature races.
Failed to compile. The trials and tribulations of batch processing.
I like how they didn't show the part where he sets it all on fire out of frustration.
In the early 50s, there was a promising synergy forming between computers and another technology. Telegraphy. Telegraphy is the long-distance transmission of textual messages, like we do every day. It has a long and interesting history, but I'm going to skip most of it and focus on one particular machine. The teleprinter. A teleprinter is just an electric typewriter with a printer hooked up to a phone. They were invented for human-to-human communication long before computers existed. You could pay an operator to send a text message to another operator over a telephone line. This was known as sending a telegram. In 1955, someone thought to replace one of the humans in the conversation with a computer. The human operator would issue commands to the computer, and the output would be printed right in front of them. This was the first instance of a command line interface. If you're wondering where the screen is, they won't use for another couple of decades. Oop. One man who saw the potential of this technology was John McCarthy. He realized that what programmers really needed was access to a computer in real time for as long as they wanted. He had this to say in 1959. Suppose that the programmer has a keyboard at the computer. Then they can try their program, interrogate individual pieces of data or code to find an error, make a change, and try again. This is what he's saying. He's saying, imagine if we could actually sit down at a computer with a keyboard. Wouldn't that be awesome? Unfortunately, doing this would leave the computer idle while the programmer pondered and typed out their program, which was unimaginably indulgent in 1959.
I remember in 1959 there was one computer in Australia.
Right.
Yeah.
It'd been very expensive to try and do something like that.
Still running the census. Still running the census. Crashed halfway through for me yesterday.
In response to this problem, his team developed the first time-sharing system in 1961. By having many users interacting with a computer at once, less processing time is wasted. If you have enough people interacting with a computer at once, no processing time is wasted. Time-sharing was very popular at universities and research organizations, but it took decades for it to replace batch processing in business. Now, it would be improper to talk about the REPL without first mentioning Lisp. Lisp is a programming language invented by John McCarthy in 1958, which emerged from his work on AI. This was the first language to contain conditionals, like if-else, recursion, so a function calling itself, first-class functions, so a function being able to accept another function as an argument or return a function, garbage collection, shielding the programmer from the hazards of manual memory management, and the REPL. Like a command line shell, the REPL was designed to be used over a teleprinter. It reads in and prints out text. However, a REPL is subtly different from a shell. Whilst a command line executes commands and prints their output, a REPL evaluates expressions and prints their value. The REPL is named after the 4 functions in this very simple Lisp program. You read the functions from right to left. Read, eval, print, loop. REPL. Each matching pair of parentheses is a function call. So what happens is the read function is executed first. It prompts the user for input. So the user types in some code, presses enter. Read returns that code to eval, which evaluates the code. It runs the code and produces a value, which is passed to print, which prints out the value, and then loop sends control back to read again. But the best way to understand the REPL is to see it in action. I'm going to use the JavaScript REPL built into Google Chrome, but these REPLs are ubiquitous. You could use them with any browser. Right-click, inspect, and you want the console tab. The console is like multi-purpose. It prints out error messages and stuff, but it also gives you a prompt where you can type code. So the simplest possible thing we could evaluate is a value. But we could also do arithmetic expressions, so 2 to the power of 64. We can also run functions. We can also run functions that have side effects. For instance, we could log hello. Notice that we get two results for this. The first is the log. The second is the evaluation of the log function, which returns undefined. This is where a command line and a REPL differs. A command line just prints output. A REPL always evaluates an expression. We can also schedule tasks. I can ask console.log to print hello in 5 seconds. It evaluates to a timer ID, which can be used to cancel the task. And then it prints out hello. This is possible because the REPL is a persistent activity. You don't fire up a REPL for every command, it's just running there in the background. The REPL is super awesome as an alternative to diving into documentation. So if you ever want to know how a language or a bunch of code works, you can just ask the REPL. For instance, if I wanted to know what this yielded, I can just ask the REPL. How about asking JavaScript the current year? All right, enough craziness. Does anyone know what this will yield? Infinity. But what about 0 divided by 0?
Yeah.
It should be 0 or infinity, right? Nice.
JavaScript versus wonky,
They're both correct.
No, they're both totally wrong.
No.
The NAND is the only appropriate answer for either of those. Divided by 0 is an infinity.
No, it is.
Divided by 0
Why is 0 divided by 0
is undefined.
Because anything divided by 0 goes forever. Because it's 0 goes to infinity.
That's how you get a...
That 1 divided by 0 is infinity. It's just
Just about a straight line, if there was a circle with a radius in it, then you've got to have to use it infinity.
Yeah,
It's just
So
a
you've
pure
got
science.
to have it, you've got to be able to have infinity as a result.
But yeah, the thing is, yeah.
I don't think you guys should look too hard for like rationality here.
No, you're right.
I'm saying this is a really good way of exploring a language's idiosyncrasies, which is absolutely necessary, especially with a language like JavaScript. But it's also a really good teaching and learning tool because you can sort of demonstrate behavior immediately and students can go and like ask it how things work. For instance, I can use the REPL to explain what it means for an integer to be safe in JavaScript. 42 is a safe integer. But what about 2 to the power of 53? If we go 1 down from that, it's safe again. So that's the limit in JavaScript for a safe integer.
How is that because I don't exploit it? Or...
I'll show you.
Okay, cool. I'm just learning JavaScript, so this is all interesting. Sorry, like as a side note to your talk.
So the REPL lets us define functions. This is just a function that increments a number by 1. Which is cool because we can start prodding it and discovering what its outputs are for whatever inputs we put in. Like if we increment the string of 1, we don't get the string of 2, we get the string of 11. And that's useful information. Like what if I put in true? That evaluates to 2. But what if I put in 2 to the power of 53 minus 2?
Okay.
So that's the definition.
Stay at the ceiling.
That's the definition of what a safe integer is. After a certain point, if you add 1 to an integer, it doesn't necessarily increase by 1.
Yeah.
They can't. It's because the number can't be represented
Yeah.
by JavaScript. No, it doesn't overflow. It just goes to infinity eventually. So you can ask JavaScript to give you a number for 2 to the power of 999, which is way outside its bounds. But it does have limits.
Can you compare numbers that are unsafe?
You shouldn't work with numbers that aren't, with integers, that you can't treat them as integers.
Yeah, okay.
There is a number, three number bars to step up to use
Sorry, what?
If you define a number, capital N number, you can
Because it's a 128-bit number or something.
compare the higher bit stage. I can check that, but I believe they're different to the default numbers.
Right.
Well, we'll have to check.
Just divide them both by 0.
One cool thing you can do with the REPL on a web page is modify the web page directly. So I'm going to give this page some historical accuracy. However, the REPL does have some limitations. For instance, it won't let you import modules using the import statement. So that makes the REPL great for writing throwaway one-liners and simple functions. Yes?
Do you still have access to the modules that were imported in the page though?
Can you import a...
You have access to the global object.
To the global, right?
Yep, which does not include modules.
Yeah,
Can you
no, right.
import a .njs file from a URI? Have you ever tried that?
And Node.js module.
No, like
What?
an ECMA module. Like an
JS
ECMA style module.
module.
Via a URL.
Yeah.
Yeah, that's the only way to do it in a browser.
Yeah. So you can do that from your REPL?
Well, you can't use the import statement
Right.
Huh?
because it gives you this error.
Yeah, so yeah, you can't use the imports. That's what the error says behind
outside
the
of
table.
module. Sorry, I couldn't. Sorry, I only got the
Oh, right, because the REPL is outside a module.
outside of module.
Yeah.
You can't enter a module.
You can't import one because a module requires some sort of context.
Yeah.
It has to know where it is in the context of the file system to make requests.
Does
Right.
this equal window now? It depends what browser you're on.
Yeah, that's cool.
All right, so the REPL's excellent for writing throwaway one-liners and simple functions. But when we build applications, we write our code as modules and save them as files. Prompt-based REPLs just don't cut the mustard for this. Lisp programmers solved this problem a long time ago by hooking up their text editors to REPLs. When I learned about this, I decided I wanted that for JavaScript. So this is my text editor, it's Sublime, and I put together a small plugin for it, which sends code to a Node.js REPL when I press certain keyboard shortcuts. The REPL's output appears in the right pane, like so. This simple configuration enables a style of programming called REPL-driven development. So let's write a module. Be on the lookout for any mistakes I make. I'm going to make a mistake on purpose, but we're going to have a debugging phase, so don't shout it out. First thing we do when we write a module is write a specification. Whoop. All right, I'll save the file. Once we've got a spec, we can write a test case. I'm going to create a dummy stream and fill it with some data. And finish the stream with null. So basically it's a stream that should read as ABC. And we're just going to print out the result. Right, now it should be obvious to everyone that this test will not succeed because we haven't written an implementation. But letting a test case fail before it passes gives us more confidence that it's actually done something. It's basically the only chance we ever get to really test our test. So let's run it. Uncaught reference error. Read stream is not defined. Well, we can fix that bug. As the data comes in, it comes in as chunks. So I'm going to create a chunks array for the data to come into. And I'm going to ask the stream to give me the chunks as strings. Every time a chunk comes in, we hold on to it. When there's no more chunks, we call our callback and join the chunks into a string. Right. Let's give that a whirl. All right, well that worked. It doesn't have any error handling, so let's test that. We're going to pass the string oops as the error message, which as you can see was uncaught. So I'll put in a little bit of error handling there. We can use the callback function directly because it takes the error as one parameter, which is the same as the listener for the error event. That's more like it. The error is oops, the string is undefined. Take that out, test it again. All right. All right, so this is a working implementation. But how can we be confident that it works for strings other than ABC? How can we be confident it works for all strings? One way is to use property-based testing, which leverages the relationships between different functions to let you write elegant tests using random input data. For instance, I'm going to import this function's inverse, which is write stream. It gets passed a string, a stream, and a callback function, and it writes that string to the stream. I'm going to use JSCheck to generate that random data and produce a test report. All right, we create an instance of the JSCheck object, which gives us a whole bunch of factory functions which return generator functions. So that one generator will just keep spewing out random integers as long as I ask for it. But what we want is some strings. By default, it gives you some short strings containing ASCII. JSCheck also gives you a check function. And we're going to say, once we've checked all of our claims, to log the output to the console. Usually it does 100 trials of random data, but we're just going to do 10 because we've only got limited space in our REPL. If I run that, nothing passed because nothing was claimed. The claim function takes a description, so and a predicate function which takes a callback called verdict, which we pass true or false depending on whether the test passed. If we run that, we see that 10 cases were tested and 10 passed. If we say false, we get a whole bunch of failures. Now the cool thing about JSCheck is you plug in your generator, which yields a random string each time, and you run it. Each failing trial tells you the value that caused it to fail. So the predicate was run 10 times. Each time it received a random string, every one of them failed, and it tells us which string made it choke. All right, so we're in a position to write the test. I'm going to use a pass-through stream, which just spits out whatever data you put in.
Is that stream library module, whatever you call them in JavaScript, is that a Node.js thing?
Yes, this is Node.js. Sorry, I forgot to mention, the REPL is a Node.js REPL.
Yeah.
Yeah, so we're in Node land.
Yeah. I was like, which web API is this? I thought streams are totally different.
All right, it's only successful if the error is null and the can't call them both string, and the string is equal to the result. And we write a string into the stream. And we don't actually care if write stream fails. This is a test of read stream, so we'll just ignore its callback. If I run that, we get a success, which is nice. But what about if we use some slightly longer strings? We're going to say, hey JSCheck, give me some strings from 0 to 100 characters in length. And we want all the characters between A and Z. 10 cases tested, 7 pass, and 3 fail. Now there's nothing immediately obvious about why those values caused it to choke. So I'm going to give you guys the option. Do we debug this with a debugger or with console.log?
With the debugger, I think.
Do you guys want to use like a, DevTools debugger or?
No, I think that with the REPL, yeah.
With the REPL, it's console.log, right? Nice. But we could use the debugger if we wanted to.
It's self-flagellation. Let's do it the hard way.
But is it the hard way when you've got the REPL like this? I don't know. All right, so the error...
I'd argue that interactive debuggers like Python, IDB, and the REPL is pretty nice. And I think you can set breakpoints and evaluate them in the REPL.
All right, we'll use the debugger.
Oh, maybe it's just IPython. Yeah, maybe it is just IPython.
All right, so if there is an error, or if the string does not equal the result, we want to jump to that in the debugger. All right. So here we are. Our error is null. And we've got 2 strings here. They look pretty similar. Can you guys see the difference?
Yeah, there's a comma in one and the other.
There's a comma in there. How did that pesky comma get in there?
I don't know.
Can anyone see the bug in read stream?
Is it to do with encoding?
Nope. What's that?
Isn't it a
join somehow? Like,
Yes, it is to do with the join.
So when you join, but
oh, is there a space?
it takes a join takes an argument, which is the divider.
The delimiter, yeah. Which by
So if you
default
make join
is...
take an empty string, that will fix it. By default, yes. By default, it is a comma.
So JavaScript makes us write an empty string if we want to just join strings, which is very sad
It just hit you.
and really tripped me up there, which is completely understandable. All right, back to our program.
And so one's ever in JavaScript, I'm still confused by the fact that you're using const everywhere. Like,
Oh, sorry, think of it as var.
Insert the strings though.
Think of it as var.
Because it's
yeah, I just thought it was a
so
mutable
buffer reads chunking.
variable
You go quick
when you use const.
The reference, the variable reference is immutable. The value it holds is
So
not.
when basically,
But why does one character trigger the end of the buffer and other characters?
Yeah. So I could have, you know, might have been nicer to use let there.
it's not a guaranteed length.
Oh.
In this case, it's all button is quick as probably is.
And I feel like I don't write down.
The first one, it's called
Recommendation I got was like use const unless you need to use something else. And so,
Yeah.
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 and that joining multiple array elements. You want to pass, the array has length of one.
All right, so if we run that, we should see if our fix worked. And it did.
This isn't the JavaScript that makes me need to have showers on.
It's because you're working with strings, that's the, it's not so much a JavaScript thing, it's the string. String is not the same as you write it in, you read it out, buffer. You don't have to throw the buffer size.
All right.
Why does your buffer size change between tests?
The buffer size isn't changing, well, your buffer size isn't changing necessarily, but the length of the data can change. It's a string, not a length of data. He's thinking of random strings of random lengths.
So the strings asking character pouring in until there's enough.
Your buffer will write in.
Okay, yeah. Sorry, no, I thought they were all the same length. I thought they were all 100 character strings.
Oh, sorry, no, here we specify a random integer as the length of the string. Yeah.
I get you.
All right, so let's do some longer strings. Let's do strings of 10,000 characters or something. And let's do a mix of...
So if you did all 100 character strings, all 10 tests would fail in this case because all 10 of them would overflow the buffer
Yes.
and get that join and get that.
Yes, all would have exceeded the chunk size
Yeah.
of the string. All right, so by default, specify.character gives us ASCII characters. But let's also put in some other fun characters. For instance, a smiley face. And let's take all the emojis between smiley face and prayer, which I think is quite a lot of them. And what about some fun technical symbols?
Vertical tab.
Vertical tab. I don't know where that is in here.
That's E11, I think.
But let's put
Breaks so many different things.
let's put the registered symbol and
It's what Microsoft Word uses for when you do like an indent for a dot point or something.
Yeah.
omega.
And the people copy pasting out of Microsoft Word into so many different things, that character just explodes it. And it's always the same one. It's always vertical tab.
All right, so let's give this a run. It worked, and we could actually go even longer. All right, so we've got strings that are 100,000 characters long that contain...
They have strings.
Yeah.
That's a good point. Probably doesn't, but up to. We could run that a few times. All right, so we've got a debugged module. All that's left is to export it. Now I'm also going to export a test function. Which could be run by some sort of batched test runner. And we'll comment this out because we don't want to run our tests every time someone imports the module. Whoop, I said read string. I didn't mean to do that. All right, so when we come back in the future to modify or fix read stream, we find all the relevant code in the same place, which is really nice. We've got the specification up top, we've got the implementation, and we've got the tests all sitting together. Notice that no matter how large this application grows, feedback can remain instantaneous whenever we go in and play with a module. This cannot be said for the majority of complex applications written today. So as programmers, our time is now the most precious resource. It's not computer time, it's not computer hardware, it's our brain time. Time spent waiting is time wasted. It interrupts our flow and stifles our creativity. So I'm wondering, what will programmers think in 50 years when they look back at our feedback loops? My guess is that they'll be horrified like we are at batch processing. That concludes the talk. If you want to learn more about REPL-driven development, here are two really great resources that inspired me. One's a video by a really funny guy holding beer, and the second one's a podcast. If you're interested in this kind of thing, like, hit me up, send me an email if you want to build your own thing like this or use mine. Any questions?